Welcome to our practice video on 15.7 on Le Chatelier's principle. Now, Le Chatelier's principle says in a nutshell that once a particular reaction, we can use this one here, is at equilibrium means that the forward reaction rate and the reverse reaction rate, R stands for reaction, little r here stands for reactance, they're equal. So this is not a negative sign, that's just notating that's a bullet point. The forward reaction and the reverse reaction, their rates are equal. And as these rates are equal, the concentrations of your products and reactants are constant. This is basically just what is happening at equilibrium, right? The forward and reverse reaction rates are the same. Concentrations of your products and reactants are constant. Now, to utilize the Chatelier's principle, we can begin to change things. So when you're at equilibrium, you can now change a few things. You can alter concentration, you can alter pressure, you can alter temperature. You can even add, random substances, maybe an inert gas to see what would happen. You do this to upset the equilibrium and make the equilibrium or make this reaction shift back to equilibrium, giving you a specific outcome that you're looking for. So usually chemists will do this, have a reaction reach equilibrium, and then alter some of these things to get more products or more reactants out of the substances that are already there. Okay, so let's look at this particular question. Consider the reaction there. My enthalpy of this reaction is negative 904.4 kilojoules. How does each of the following changes affect the yield of NO at equilibrium? So NO at equilibrium, this is what we're looking for, or looking at. Our answers will be either increase, decrease, or no change. So A, if I increase NH3, if I increase the concentration of NH3, what happens to the concentration of NO? That's what we're being asked here. Well, Le Chatelier's principle says for concentration, if I increase NH3, now NH3 is a reactant. If I increase NH3, I upset the equilibrium. So this reaction is going to want to get back to that equilibrium state. And the only way to do that is to get rid of the NH3 that was added. So when it says, increase NH3, literally think of the chemist adding more NH3 into the reaction flask, right? So if I add more NH3 in, the reaction is going to want to get rid of the NH3 that I added in. The only way to get rid of it and to get back to where you were is to use it. The only way to use NH3 is to go through the reaction. NH3 is going to be used with the O2, creating your products. So when you increase the concentration, equilibrium is going to shift to the opposite side to get rid of what you added. So NO, since it's on the opposite side, it's going to increase as NH3 increases. B, we increase H2O. So if I increase H2O, H2O is a product. We're looking at how that's going to affect NO. So now, the clean slate here, H2O here. If it were to increase, I want to now, equilibrium gets upset. I want to get back to equilibrium, so I have to get rid of the H2O that I just put in there. You know, the only way to get rid of H2O is to use it. So H2O is going to be used with the NO, producing more reactants. So since NO is on the same side as H2O, they have to be used together. You can't just get rid of H2O by itself without the facilitation of NO there. So you have to use it together. In this case, NO is going to decrease because as the product H2O has to be used, it's going to be used with NO, NO's concentration decreases. Okay, that's the basic gist of increasing or decreasing concentrations. So now let's do another example here. C, if we decrease O2, what does that do to NO? Okay, so decreasing O2, get a clean slate. We have to look at O2 here. It's a reactant. If this decreases, equilibrium is upset. We're no longer at equilibrium. Thus, we have to increase the O2 to get back to equilibrium. So if I took it out as a chemist, the reaction is going to increase it automatically to get back to that equilibrium state. So to increase O2, the products here are going to react together to produce more O2. That's what the reaction will facilitate. So NO, in this case, is going to decrease because it's going to be used to create more O2. D, decrease the volume of the container in which the reaction occurs. So if I decrease the volume, so in Le Chatelier's principle, decreasing the volume or increasing the volume changes the pressure. So if I decrease the volume, I make things tighter. I make things smaller. So if things are smaller or tighter, you can think of this chemical equation as kind of like a vessel here, right? If things are tight and small, this is like one big vessel. So we have to think about the number of moles of gas on each side. We got 4 moles, 6 moles, total of 10 moles of gas there. Here we have 4 and 5, total of 9 moles of gas on that side. As you squeeze this container and decrease the volume, you upset the equilibrium. And to achieve equilibrium, as you decrease the volume, I'm going to write a side step here. Decreasing the volume increases the pressure. So as that pressure is increased, the reaction is going to want to relieve the pressure. It increased, it wants it to go back down so it can get back to equilibrium. So it's going to take the side with more moles and get rid of some of those. Equilibrium is going to shift to that side. So as pressure increases or volume decreases, equilibrium shifts to the side with fewer moles. So just think, everything is getting tight. This side has more particles. These particles are more likely to collide because I have 10 moles versus 9 moles. Think that's one more factor of Avogadro's number. That's a lot more particles, even if it's just 1 mole difference. These particles on the right side, my products, are more likely to collide to produce my reactants. So NO is going to decrease because it's going to be being used here. Okay, so E, adding a catalyst. If I add a catalyst, in short, there's no change. And there's no change, we can kind of use our energy diagram, potential energy diagram, or um, I think we said progress before. So for this one, we, start at, this is an exothermic reaction, right? So we start at some energy value of my reactants, some activation energy, and I get to my products. If I add a catalyst, that catalyst just decreases the activation energy. So this is with the catalyst. The catalyst speeds up the rate of the reaction. However, it speeds it up in either direction. So in the green, if I'm going from reactants to products, it's that fast. That much energy is needed. If I'm going from products to reactants, it's still at the same catalyst barrier. Nothing changes really. So there's no overall, you know, net shift. Okay, so no change with the catalyst. And F, increase the temperature. So if we increase temperature, we have to look at this reaction. I'll rewrite it. And we got to think about how heat affects it. So my delta H of the reaction is negative. The value here doesn't even matter. It's just the sign of the value that really matters. If it's negative, that means this equation of this reaction is exothermic. If it's exothermic, you're going to have a net release of heat, meaning heat's going to be present in excess at the end of the reaction with the products. So I like to even think about putting heat as a reactant or product here. So since it's an exothermic reaction, you're going to release more heat than you absorb. So I'm going to put here plus heat, meaning it's exo. Heat's going to be released at the end of this reaction. Okay, so that's how you can use this delta H is negative 904. Just keep putting it as a reactant or a product. In this case, it's exothermic, so it's a reactant. If it was endothermic, it'll be over here. Sorry, it's exothermic, so it's a product. If it were endothermic, it would be a reactant over here. Okay, so now if I, as a chemist, increase the temperature, if I increase the temperature, equilibrium is now off. To get back to equilibrium, I want to remove some heat because I just added heat, so the reaction is going to remove heat itself. To remove heat, you got to think about which direction of the reaction does that. Does the forward direction remove heat, or does the reverse direction remove heat? Well, the forward direction, this way, it produces more heat because plus heat. I get heat if I go in the forward direction. In the forward direction, I will produce NO, H2O, and heat. So the forward direction makes things hotter. The reverse direction, here in yellow, the reverse direction will make things cooler. I use heat with H2O, with NO, producing O2 and NH3. So in the reverse direction, you use heat. So if the chemist increases the heat, the reaction is going to wants to get rid of it. The reaction is going to get rid of it by using it. So the reaction is going to take heat with H2O, with NO, and produce more O2 and NH3. So NO is going to decrease. And now lastly, I've added one here. I've added G, adding a noble gas. So overall, if I add a noble gas, let's say I add argon. there's going to be no change. You can think of it in a very simple way where, noble gases are unreactive. They're not going to interact with the actual substances there and chemically influence the chemical reaction. And because they don't chemically influence the chemical reaction, they will not influence the equilibrium expression, products over reactants, because they won't be here in the actual reaction. They won't be in here. So there's no change overall. If you want a more technical, explanation, then you can think of it this way. Because some guys are, going to think about this a little more deeply. If I do add argon, let's think about what things are happening. I am actually increasing total moles. I'm adding more stuff in there. So things are tighter. So you might think, well, if things are tighter in there, wouldn't it influence or make things collide more frequently? Wouldn't it bother something? Yeah, it does change your total pressure. So total pressure of that container does increase. Now, we have to think about some things from, back in chapter 10, we were talking about gases. What doesn't change? My moles of reactants and products do not change. Just because you add another substance in doesn't actually change the other already existing reactants and products there. We have to remember that with the ideal gas law, Pivnert, and this only applies at constant volume, by the way. What we're talking about here means we have to think about this. There's no change if volume is constant. If volume changes, then we have a different problem to face. But you'll worry about that as you go into the collegiate studies. So V, R, and T in Pivnert, they're constant. So really, we're just looking at pressure and how it's influenced by N. So pressure only depends on the number of moles. Now, if my total pressure increased, as I said over here, it's because my total moles increased. So it was a proportional increase. And just as I can do this for total pressure, if I had, my gas, its pressure depends on number of moles. Now, by adding argon, I did not change the number of, that should be an N. I did not change the number of moles of NO by adding argon. So the pressure doesn't change. So there's no change here in pressure since I didn't add any NO. Thus, there's no change in NO. It's concentration. If we think about your K sub C or K sub P, whatever you want to think of, K sub P or Q sub P, these are based on the pressures the partial pressures of each individual gas. And since argon would not show up in this expression, argon has zero influence on the equilibrium. And also, since total pressure, which argon influences, doesn't show up in your equilibrium expression, argon has no influence on equilibrium. All right, gentlemen, hope this helps. Adios.